Tracy always gets cupcakes for her birthday.
I just saw her with one. We need to go sing to her. Oops, they may be getting ready to be pretty embarrassed because there's actually no reason to believe that it's a birthday. What happened? Well, we're told cupcake, and we're told that birthday implies cupcake. It appears that what they did was to use a rule called converse. The converse says, well, if you have birthday implies cupcake, you must also have cupcake implies birthday. Now, just looking at this particular situation, we know that's not necessarily true. Maybe it's just National Cupcake Day. Having applied converse, they used a sound rule modus ponens and said, well, from cupcake and cupcake implies birthday, we're good with birthday. The problem in the reasoning happened at step 3 with converse. Converse isn't a sound rule. It gets us conclusions that aren't justified. And let's see why we know that that's the case. Here's the truth table for converse. It says, if it were to be a sound rule, if it were to be a tautology, then we'd have to have the case that B implies C is logically equivalent to C implies B. And if that were true, then this last column would contain all T's. It doesn't. It contains 2 T's and 2 F's. And in fact, the 2 F's happen exactly in the case where B and C have different values, where it might be the case that there is a cupcake and not a birthday. All right, so converse isn't a sound rule, and if you use it, you may derive junk. Now we know why that particular mistake happened.
Students who love pizza always go to Ziggy's.
But I hate pizza, and you're telling me I can't go to Ziggy's? Oops, they may be getting ready to go hungry unnecessarily. Let's look at what went wrong with the logic. We're told that if you love pizza, you go to Ziggy's. And we're told not love pizza. What can we get from this? They got not Ziggy's. How do they do that? Well, maybe try to apply modus ponens to 1 and 2, but modus ponens doesn't do that. In order to apply modus ponens, we'd have to have love pizza, and we don't. So that isn't it. What else might have happened? It looks like maybe what they did was to say, well, if we know love pizza implies Ziggy's, maybe we know that not love pizza implies not Ziggy's. I've written question mark here because there's no rule that actually does that, but let's imagine that they did. Well, then they'd get the rest of the proof, right? Because then modus ponens from 2 and this fictitious 3 would get us not love pizza implies not Ziggy's. There you go. But this rule is also fictitious. Let's see why. Let's look at what the truth table would be if it were a sound rule. It would look like this. We would have to show that L implies Z is logically equivalent to not L implies not C. And look at what we get. Again, we get 2 T's and 2 F's. Again, that we get an F exactly in the case that the 2 inputs, in this case loving pizza and Ziggy's, have different values. So that's where the trouble was. Let's summarize what we know about cases where we're told something of the form P implies Q. So you tell me P implies Q, that's premise. Where can I go from there? We know that we can use the contrapositive to derive not Q then means not P, and that's sound. Let's look at the 2 other things that just happened. The one we used for cupcakes has a name, it's called converse, and it says that you can go from Q backwards to P, and we just showed that that's not sound. And the one that was used for pizza is the one that said, well, then we can go from not P to not Q, and that one also isn't sound. So we have to be very careful when we're given something of the form P implies Q, that we use it in one of these 2 forms, and that we don't jump to conclusions with one of those unsound forms.
If you're in line and you've got a ticket, you'll get into the game.
Great, I'm first in line, I'm in. Gosh, they may be about to get really disappointed at the front of the line. Let's see what went wrong. We'll call this one wishful thinking. What we're told is in line, and that in line and ticket gets you in. And the reasoning somehow got to get in. Let's try to imagine how they might have done that. Modus ponens with in line and what? 2? But that doesn't work, right? Because modus ponens, if we want to use it with 2, we've got to have inline and ticket. Well, what might they have done here? Suppose that one were to reason as follows. If I actually knew that you were inline and had a ticket, then I could use simplification to say, well, then, in particular, you are inline. Suppose they did that here and derived from inline and ticket implies get in, simplified this piece, the part before the arrow, to inline to derive 3. Well, then we can use modus ponens with inline and 3 and derive get in. But what went wrong? In a nutshell, you can't do surgery with inference rules. You can do it with identities, but not with inference rules, inside an assertion. So it's not okay to claim that if inline and ticket gets you in, then inline alone gets you in. It is sufficient to say if inline and ticket are both true, then inline is true. But you can't do it down inside an expression like that. If you do, you'll get conclusions that don't follow from the premise. Well, Mr. Aristotle, we're hoping that you're proud of us now. We know what to do. We're not going to make the cupcake mistake. We're not going to make the pizza mistake. And we're not going to make the ticket mistake anymore.